Okay, so so we're going to prove the Picard-Lindelöf theorem, and we'll see, it may take us, we may need to continue on it also on Tuesday, and then when we're done with it, we will just do review on Tuesday, but let's see how far we get. So the Picard-Lindelöf theorem is the following theorem, and it says that it's a ODE, so it's what's called the ordinary differential equation. And so again, a differential equation is something about an unknown function and its derivative, right? So a differential equation just means it's an equation. So this here means that it's an equation in an unknown function and its derivative. Ordinary, just as we talked about last time, ordinary refer to that is just of one variable, okay? And so the ODE that the Picard-Lindelöf theorem is about is, so the unknown function is y, and the ODE is this, that we want the derivative of this unknown function to be equal to a function of the unknown function plus another function that just depends on x. So y here is the unknown function, and y is a function of x. Right. X is a real number, right? And it's just a, yeah. So this is the differential equation, and then we have some initial condition. So at 0, we want it to take a value a, okay? So this is the differential equation, and what we assume here is, so f and g are function on R, and you should think about those as being known, and they are, and f here is differentiable, and the derivative is continuous, and g is just continuous. Doesn't need to be differentiable. And the Picard-Lindelöf theorem is, so again, the Picard-Lindelöf theorem is the following, that given f g as above, and sorry, and a was this constant, it's just a real number, as above, there exist delta greater than 0, such that, and a solution y defined on the interval from minus delta to delta, and solution y to the ODE, right? And so again, meaning that is solution, that means that at 0 it takes value a, and then it's satisfying that equation, okay? And moreover, and I'll get back to that, but we won't you know, it's quite possible. I won't get to that today. Moreover, solutions are unique. Okay, and so this is like a standard problem when you're looking at differential equations. You have a differential equation that may describe something in nature, and you wonder, does this equation have a solution? And if it has a solution, are solutions unique? Okay, so this is what this answer in this case. And the interesting thing, or part of the interesting thing, I mean, so this is a fundamental question used all over science and engineering. And one of the interesting things is that it uses, the proof of this uses metric spaces. And so the proof has been used, you know, various versions of the proof have been used to prove existence and uniqueness of various differential equations. So the proof uses the theory of metric spaces, which is sort of surprising because it seems to have nothing to do with metric spaces. And so it uses, in particular, the metric space that it's using is the continuous functions on some interval here, right? And on the space of continuous function, we have the metric that we talked about. The metric, so if f and g, sorry, f is so bad because it's the and g also. Let's call it h1 and h2. Suppose that these are continuous functions, h1 and h2 are continuous functions on an interval like this. Then the distance is this that we have considered various times. This is just the maximum over x in this interval here of f of x, of h1, sorry, h1 of x minus h2 of x, and then the absolute value of that. Right. So this is the distance on the space of continuous functions that we have looked at a lot. Okay, and it's actually not quite this space, as I mentioned last time. It's a ball in this space that is using. Right, okay. So what do we need about this metric space? So one thing we've proven a couple of lectures ago is that this space here of continuous functions with this metric here is Cauchy complete. So we're going to use that, okay? Another thing we're going to use is this notion of contracting map. So another tool will be that of a contracting map. And so, and remember, this is a number of lectures ago. We talked about a contracting map, but we need a more general notion of contracting map because when we talked about it, we talked about a map from R into R. And then we used this notion of contracting map to finding zeros with using Newton's method, okay? But here we're going to use it for something different, and so we need a more general notion. So suppose that, contracting map. So this is the general version, as opposed to the version that we talked about already, that was for for the line for R. So contracting map, sorry. And so this is, so you have a metric space XD. This is, it could be like this, but it also just could be any metric space. And then you have a map from this metric space into the self. And T here is said to be contracting. If there exists a constant C less than 1, such that if you're looking at the distance between the images, then they are squeezed together. So this distance here between the images under the map is less or equal to this constant that is less than 1 times the distance before you apply the map. Right, so this means that under the map, things get closer together, right? So that's a contracting map. And so now we proved a theorem when we did the Newton method. We proved a theorem, but we needed about fixed points. And we need a generalized version of that. So if you take a map just in general, from a space to a space, then a fixed point is a point x in the space, so that t of x, so t leaves x invariant, so t of x is equal to x. That's a fixed point, right? Okay, and so now if you have a contracting map, so if t here is contracting, then t can have at most one fixed point. Why? Because suppose that x, so if x and y are both fixed points, well, then you have that t of x is equal to t of y. Sorry, t of x is equal to x, and t of y is equal to y, right? And so now you have that the distance between t of x, let me make a little more space. Then you have that actually we just continue down here. So that the distance between t of x, comma t of y, the map is contracting, so this is less or equal to this constant times this here. On the other hand, they're both fixed points, so t of x is x, this here is x, and this here is y. So if we write this out, so this is x comma y, and so you see that this thing here is some constant less than 1, strictly less than 1, times itself. So this means, of course, that this number here, this non-negative number, must be 0. And so this, of course, implies, by the actions of a metric space, that x is equal to y. Right? So a contracting map has at most one fixed point. Now, the other thing is that if you take a metric space, right, so this here is Cauchy complete. So now I'm going to take a Cauchy complete metric space. So it could be continuous function on some closed interval, and that's how we will apply it, but it works more generally. So we have the following theorem. So if this here is a complete, Cauchy complete metric space, and T from X into X is a contracting map, then T has a unique fixed point. We know it only have at most one, so the statement really is that it has one, right? So it has a unique fixed point. Okay, so let's try to prove this. And you might remember, and if you don't, that's fine, but you might remember how we used it in the Newton methods. Because the Newton methods was like, it was a version of this on R. So you had a map from R to R, and to find the fixed point, and so you wondered what you were there in the Newton methods was something about finding a point where a function vanishes, right? And that was set up as a fixed point theorem. And so what you did is you made a good choice. I mean, a choice that looked reasonable, right? This is not exactly where the function vanishes, but something that looks close to where it vanished. And then you took the image under the map and you iterated this. And so it's the same we're going to do here. So, and this time we don't even need to make a good choice. So we just take, let X here be any point in the metric space. So you're just fixing some point in the metric space. And now you're looking at, the sequence X, T of X, and then you apply T to T of X. So this is, I write this as this. And then you apply T to T squared of X. So that's right like this. And so you keep applying T more and more times. Right, and so this gives you a sequence, and so on. So this gives you a sequence, okay? And now the claim is that this sequence here, so claim that this sequence here converge to, right, so it converge, and the limit here, this here, is a fixed point. For T. So that's a claim, okay? Now, so we wanted to prove first that it's converging. Okay, so we're going to prove first. So we'll first show that Tn is a Cauchy sequence. Okay, so now let's look at, so we're supposed to look, if you're looking at if you try to prove that something is a Cauchy sequence, then you're looking at the distance between elements in the sequence where both of these elements is sufficiently far out, right? That's what you're supposed to look at. And so let me write the M here. So I can think about one of them as being further out than the other one. So I'm going to think about M here as being N plus some number K, right? Some integer K, right? And so I'm interested in estimating the distance between Tn of X and Tn plus K of X. Okay. Now, in order to do this, let me start with something simpler first. Let me look at the distance between t of x. Let me look at the distance between t L of x and t L plus 1 of x. Okay, so two consecutive elements in the sequence. Okay, now I can sing it. So this thing here, well, this is equal to the distance between t of t L minus 1 of x and then t of t L of x, like that, right? I can write it like that, right? But now, of course, so you see here, there's some element in x, so in the space x. Here's another element. They both have t applied to it. T is contracting, so you get c t L minus 1 x TL of x. So you see that if you take two consecutive elements and you're taking the distance, then it's bounded by this constant c times, right, where you have one less, where you have applied t one less time on both, right? These are again consecutive elements, but the highest one is one less, right? And okay, so now if you iterate this, okay, so iterating this, so let's see, maybe, okay, maybe let me wait with iterating. Let me just look at what we need. So we have this in here, and this here I can write as so here you see, here I can write this as t, the distance t, and then t n minus 1 x, and then t n minus 1 plus k x, like this, right? And so here I can use the same trick, that it gets c, and then d t n minus 1 x, comma t n minus 1 plus k of x, right? And this one here, I can keep going like this, right? I can keep going until there is I've used up all my n's, right? And so I can keep going, and so this is less or equal to c to the n. And then the last one I get is I get x, and then I get tk of x, right? I want to show that this thing here becomes small as long as n, remember k is a positive integer, as long as n is sufficiently large, right? So I need, but this is a hopeful sign, because when n get large, this here get really, really small, right? But I still need to estimate this here, right? Now, so how do I estimate it? I'm using what I did over here. So so you're looking at, so you have the distance between x and tk of x. This thing here, I can use this triangle inequality. So I can say that this is less than dx t of x plus dt of x t squared of x plus dt squared of x like cube of x, and then all the way up to d t k minus 1 of x t k of x. Right, so this is just the triangle inequality, right? Now, this may seem rather bad estimate, but let's see how bad it is. So, right, so now this first thing here, I'm just leaving it. I can't do anything about that. So I need to just take that. This one here, so I'm using this with between two consecutive. So in this case, it's just bounded by c times d x tx, right? And the next one here, this one here is bounded by c squared d x tx. And the next, right, and so on, up to this one here is bounded by c k minus 1 d x t x, right? And so you see that now this here factor out. So this here is, so this factor out. And then in this bracket you get 1 plus c squared plus all the way up to c k minus 1. But this is a geometric series, right? This is a geometric series. And this is certainly less than when I take, remember c is strictly less than 1. So it's a geometric series, it's a convergent geometric series. So this here is less than d x t of x. And then the sum, well, it's less than when you're summing it all the way to infinity. So this is less than 1. This is the sum of the geometric series. C is strictly less than 1. Right, C is positive and is strictly less than 1. Okay. So you see now that we have, right, so we have that, so what we were interested in is, we were interested in saying that as long as I choose little n sufficiently large, then this thing here must be very small, right? And we know already that it's bounded like this, and now I fill in this, and you see this here, so this means that this is less than Cn, and then what you get here is 1 minus c, and then times d x t of x, right? X is fixed, and so you see that when little n is sufficiently large, then this whole thing here is as small as you want, right? So this means that what we have proven here is that this sequence here is a Cauchy sequence. So we've proven that, okay? Now, of course, this is where the assumption comes in, that this metric space is Cauchy complete, right? So since X, this metric space is Cauchy complete, and this sequence here is a Cauchy sequence, it is convergent, right? Yeah.
I'm sorry, just back to that end of that quickly.
Yep.
Are you able to explain again how we got that? How we were trying, did we find a bound for the dx, tx, or we're just saying that?
Right, so I'm saying that x is fixed. You pick any point you want, and I claim that if it may be a very bad candidate for the fixed point, but it doesn't matter. It's okay. It may just take you longer to get to the fixed point, but you fix x, and then you're looking at this sequence. And then I claim that this sequence will be a Cauchy sequence, right? And so x is fixed, and so we have this inequality here. And what we need is that when little n is sufficiently far, large, then for all k is positive integer, right? This here is like further out than n. Then for all k, and this should be independent on k, this thing here is small. But this is just...
To get rid of the whole thing from the previous step was now it's not a tk of x, right? So
yeah, so x, since x is fixed, tx is fixed. So this is just a constant. Yeah. Okay. So right. So what we have proven is that we have this Cauchy complete metric space, and we have this sequence x was fixed again. That is a Cauchy sequence. And so since this metric space is Cauchy complete, this is convergent, and I can denote the limit. So I just call the limit x infinity. Right, so if you have this. Now I want to show that so the next claim is that x infinity is a fixed point for t. Okay. So if I'm looking at this sequence here, suppose I take this sequence, and suppose I take t of this sequence. So if I take t of this sequence, this here is nothing but the next element in the sequence. So this one here will still converge to x infinity, right? Because it's just shifted by 1. But then on the other hand, so now if you're looking at so you have that if you're looking at t, so we want to prove that right. So now if we're looking at t of x infinity, the distance between t of x infinity and t n plus 1 of x. Suppose I'm looking at this distance here, right? Well, this here I can think about as the distance between t of x infinity and t of tn of x. But here there are now both of these elements. You can think about this as just some element, apply t to it. Here there's t applied to that. So this is less than the distance x infinity to t n as a constant c less than 1 in front. So like this, right? By the contracting map property. But now you see that as n go to infinity, this thing here goes to 0, right? So this means that this thing here converges to this point, right? So you have that. So you have that. You have that if you're looking at right again as n go to infinity, since tn of x converts to x infinity, then we have that the distance, this is equivalent to that the distance here goes to 0, and then by this inequality, it means that the distance here, tx infinity and tn plus 1 of x goes to 0, right? And so this means that this is just some fixed point. It means that this sequence here, so this implies that this sequence here converts to t of x infinity, right? But on the other hand, we already observe that this sequence also converts to x infinity, right? But you so it converts to this and it converts to that, but it can only have one limit, so those two things are equal. So you conclude that x infinity is equal to t of x infinity. And so x infinity is a fixed point. Right, so this proved this theorem. Right? And again, we already knew that the limit was unique, right? Okay, so now how is this related to the Picard-Lindelöf theorem? And so it's related in the following way. And again, this is something that have been used to solve a lot of differential equations. And so we need to define space and a map. The space is initially, but we have to restrict it. But initially, let's think about some continuous functions on some interval. Let's start with just continuous function, but it's not quite going to be the space. I will have to look at a smaller, yeah? Right, that's a good question. So that's right. So this comes with this Newton method. So we used this contracting mapping for R in the Newton method to find a 0. Okay, and to some extent, I mean that was a great idea. Newton was a pretty famous guy for a good reason. But in a way, this is more ingenious, I think, because it's like, metric space. What the hell does that have to do with differential equation, right? And the reason why in the other one we had to restrict it was that the map we defined wasn't contracting everywhere. It needed things to be pretty close initially for there to exist a C strictly less than 1, right? So that's where it came in. It wasn't really because yeah. Okay. So now again, so we need to relate this, that seems to have nothing to do with differential equation. We need to relate it to the differential equation. So again, what is the space, the metric space that we're going to look at? And again, it's not exactly this, but it's just a subset of it. So it's this space and with the usual metric that we have talked about, right? That is going to be the metric space. Now, what is the map T? And so the map T is, so T here is going to be a map from continuous functions into the space of continuous functions. And it's going to be defined as follow. And I'll come to this in a second. So T of x, T of y. So y, think about y as being a continuous function on this interval, right? And T of y is now equal to a plus, and then the integral, and then, right. Then the integral, so this is so T of y is an element here. This one here is also supposed to be an element here. So this is a function. So we want to find out what the value is at x. And it's a, this constant a, plus the integral from 0 to x, and then of f of y, plus g of x. And this here is a function of x, right? Also, it's like this. And I shouldn't write x because I use now x up here. So I write it like that, df. Okay, that's how the map is going to be defined. So again, if you take, so y here, so y is a continuous function on this interval. And I will have to restrict it. And this is exactly when you're asking what, in Newton's methods, right? Why did we have to pick this good choice? It's exactly like this, that this map is not contracting on this whole space, okay? So we have to, in a way, we have to do the same stuff. We have to make a good choice first. And so that's why we have to restrict the space, okay? And it actually is, I mean, it's part of the beauty is that it's pretty much optimal, this stuff, this sort of general principle. We can come back to that. So this is the map T. And so the first thing that you observe is that T, so this gives you this function here, right? Remember that, so if y is continuous, g is continuous, if y is continuous, f is continuous, everything here is continuous. And so this means that by the fundamental theorem of calculus, this function here is actually even differentiable, right? And the derivative, this is just a constant. So this function here is differentiable, let alone continuous. So it's definitely in the space. And the derivative of this map by the fundamental theorem of calculus so by the fundamental theorem of calculus, the derivative is just what is inside here. So this is just f of y plus g of x. Right? And if you want to write x in, then it should be like this. Right? So that's, so, and then one more thing you observe, which is also immediate, that if you take a continuous function like this, and now you evaluate this at 0, right? If x is 0, well then this integral, it's over just a point, so this here is 0. So this means that the value here is a. Right? Okay. And so now, the next thing you observe is that so the next thing we observe is that that if you have a fixed point, so if, I mean, I think this is another nice thing is that, that the way it's set up is that you just need to use continuous functions, right? But of course, if you want a solution to this, it means that the function must have a derivative, yeah. Yeah, we don't know that yet. I mean, that's a major point, actually, right? And again, just like in the Newton's method, we have to restrict where we're looking at it, yeah. Okay, so, but the first thing I want to observe is that if y is a fixed point, well then t of y is equal to y. And so what does this mean? Well, the derivative, so it means that if this is the case, right, then we have that t of y is of this form. So it has a derivative, and that derivative is this, right? So this means that y would have it, because y is equal to this. So y is differentiable, and the derivative is equal to this. And we always have, whether it's a fixed point or not, we always have that t y of 0 is A, and since it is a fixed point, this is also this. So you see that if it is a fixed point, then it is a solution to the differential equation. Okay. Now then, the point comes in. The key point comes in with proving that the map is contracting. Okay. Okay. And so we need to show that T is a contracting map. Okay. So I define, so set, I have to define a number of things because again, I have to, it's not, T is not going to be contracting on the space of continuous functions. So I have to look at some subset of continuous function. And the right subset is just a ball. It's a closed ball, so it's going to be, so we're going to, maybe I'll just say first, that we're going to restrict T. So T here will be restricted now to, we will think about it as a map on some ball into itself. But it's not at all clear that this map takes a ball into itself, okay? And what do I mean by balls? I have this bar up here. So I just means that this thing here is going to be the function y that is continuous. And then it's not quite going to be this either. I have to restrict, but I'll get to this in a second. So at the moment, you can think about it as being continuous function on the interval, so that the norm of y at each point x is less or equal to r. And this bar here refers to that that equal is also allowed. Right? Now this here is really like the board. By these are functions. If you're thinking about the function in the space of continuous function that is constant 0, right? Then these are the functions whose distance, this is the same as the space of continuous functions, whose distance to the constant function 0 is at most r. This is the 0 function, is less or equal to r. Sorry, this is getting a little smaller over here. Right, so it's just, okay. And again, it's going to be, I will have to restrict the interval here to make sure that the map is contracted. So, but first I want to define this radius here, okay? And so the radius is, so I'm setting r here equal, a was just a constant. I take the absolute value of a and I add 2 to it. Then I define two other, and there's no way around it. You have to define, we will require to define several constants first. L1, capital L1, is going to be another constant. It's going to be the maximum. And then you take of over z, where z here is less than r, and then you take the value like this. Okay? Remember, f is continuous. So if I'm looking at where the norm of x is less or equal to some constant, then the maximum is achieved on this. Right? So this is just some real number, positive real, non-negative real number. And then I define L2 to be the maximum of maximum on this unit ball here, on where norm of x is less than 1 of g of x, like that. Okay. And now, what I want to do is, so the first step is the following. So first step in the proof is to prove the following, that there exist delta 0. This is not the delta that I will use eventually. I will have to restrict it further. There exists delta 0, so that if you're looking at the space, if y here is in the space of continuous functions on this interval here, then t of y, sorry, if y is in this here, and y is in the unit ball, and not in the unit ball, that y here is less or equal to r. Right, so it's a continuous function on this interval, and the norm is less or equal to r. So this means that, so this is of course the same as saying that y is in this ball here, when I'm now thinking about this as a space. But you can forget about that if you want. It's the same. Okay, and I want to show that t of y is in the same space, right? So I want to show that t of y at each x here, the norm is less or equal to 1. Right. Then if I have that, I already know that this function t of y is continuous. It's actually even differentiable, right? But it's in particular continuous. And if I have this, then I know that this space is taken into itself, right? Okay. So now how do I do that? So that's where I need to restrict the interval that I'm looking on. And again, we'll come back to it, but there's a good reason to restrict, that we have to restrict. Otherwise, it couldn't possibly be true. Yeah.
For it to be contracting, do we need it to be strictly less than?
So remember, contracting means that there exists a constant c strictly less than 1. This here had nothing to do with the constant c. This here is just the space that we're looking at the map on. Okay, and the reason why I make here, so this have nothing to do with that c, but the reason why I want this less or equal to is that I want to have that the space is Cauchy complete. Okay, sorry. So let me just try to make that clear. So I have, to get a fixed point for a contracting map, you need a space that is Cauchy complete, right? That when we prove this for the metric space. We have a good candidate, right? We have the candidate of continuous functions on some closed interval like this, right? This is Cauchy complete, right, with the usual metric. But I'm not going to look at that space, because my map is not actually contracting on the space. It's contracting on a subset, right? And so I need that subset. So in the end, I sort of, I'm not working on this, but I'm working on a subset, right? And I need that subset to be Cauchy complete. So basically what I have is that this here is the giant metric space I start with. Then I'm looking at a ball in this. And if I take the closed ball, and it happened to be at the origin, but it could be just at any point, right? If you take a metric space and you're taking something like this, if the metric space is Cauchy complete, then this subset is also Cauchy complete. But this require I have less or equal to, right? Because else it could kind of convert to something where you got equality, right? So that was why I do it like that. Okay, so let's see. So we are trying. We have already defined this radius, capital R, and then we have these two constant L1 and L2. And what I need to prove is the first step here is to prove that if I'm going to look again, so the first step is that I need to restrict. So I need to restrict, so I'm going to look at these spaces of, this is a subset of the continuous functions, and I need to prove that if y is in here, then the image is in the same space. Okay? And so this is the statement that if y is continuous, the norm of this function is less or equal to r. So at each point, each x, the absolute value of y of x is less or equal to r. Then you have the same for the image under t. We already know again that the image under t of y is continuous. Okay. Okay. And so, what I can do is I can restrict my interval. So I will restrict the interval as follows. So I'm going to pick delta 0 to be the minimum of 1 over L plus 1. L is non-negative. In principle, it could be 0. I don't want to worry about that, so I just add 1. And L2 could also be 0, although it's pretty unlikely that any of them are 0, but I'm just, to be safe, I'm just adding so I don't divide by 0. So that's why, and the first thing is that and then I'm going to look at the interval from this, and this is not going to be my final. I will have to do some further restriction. But I'm going to look at this interval initially, okay? And the one here just comes in that I want this here to be a subset of this unit interval, okay? Okay. So now let's try. So now we are in good shape here. So now let's look at t, y, and we need to estimate this at each x, right? And we want to say that the norm is less or equal to capital R. But let's just look at what this is. This thing here is equal to this function t of y is defined to be a plus the integral from 0 to x of f of y of s plus g of s ds. And then I have to have absolute value like that. And now I can just use the triangle inequality, of course, sort of trivially. I get absolute value of this, and then plus, and then the integral here like that. Oops. And then I can just take this absolute value in under. So I get less or equal to a plus, and then the integral, and then the absolute value of f of y of s. And here I can also take the absolute value using the triangle inequality on each individually. So I can write it like this. Now, this is where I use, so s here will have to lie between 0 and x, right? And so x is between, let me just draw it here. So here I have 0, here I have delta 0, and then I have, this is 0, and here I have x, somewhere x, right? But since, right, so this means that, this means that, so here you have x, but x itself, x has to lie between delta 0, minus delta 0, and delta 0. And s has to lie between 0 and x. So this means that s here lies between, x will lie in this interval also, right? But now you see that so now if we're looking at, so we have t of y in x, again, remember that x here is less than or equal to delta 0. So we have that this thing here is less or equal to a plus, and then the integral from 0 to x of f of y of s plus g of s ds. Right. And the first thing I observe is that s here is also, just because x was in that interval, you also have that s, because x is in that interval, s is also in this interval. The second thing I observe is that I'm assuming that the function that I start with at each point have norm less than r. Now, if I'm using these two things, then I have that, so this means that g of s, this one here, this is how we defined L2, right? Because this interval here is contained in the interval between -1 and 1. This here is contained in the interval between -1 and 1, right? So we have that g of s is less than this L2, less or equal to L2, right? The second thing we observe is that because we have this here, for each s, we have this, then it means, you see, by the definition of L1, that f of y of s, this thing here, is less than L1. Okay? L1 and L2 are now fixed numbers, right? And so you see that this second thing here, I can bound this thing here by, so this is less or equal to a, and that should have been an absolute value. Somehow I lost it when I copied from this line. A, absolute value of a. And then on the first one here, the length of this interval, but that is of course bounded by delta 0, right? So this is plus delta 0, and then the maximal possible value of this, that would be L1. And then likewise, the length of this interval you're integrating over is at most delta 0, and this one here cannot be larger than L2. So you have this, right? And now remember what delta 0 was, and I will just, I have it, I think, on the board below here, but let me just write it here. This here was what delta 0 was chosen to be. The minimum 1 over L1 plus 1, 1 over L2 plus 1. Okay? So now we have that this thing here is less than, this here we just keep. This thing here, well, delta is in particular less than this thing here. So you see that if you plug in this, so it's like plus 1 L1 plus 1 times L1. Likewise, over here, you're using this, so you're getting 1 over L2 plus 1 L2. And now you see that this thing here is less than 1. This is less than 1. So this is less than A. It's actually strictly less, but it doesn't really matter. A plus 2, like this. Okay. So this means that, so then, but this here was exactly the definition of capital R, right? And so you have that, and when I copied it over, I also forgot to put absolute value sign here, right? So you have that so the conclusion here is that if y here is a continuous function on this interval here, and the norm of y at each point is less or equal to r, well, then you have that t of y at each point is less than r. Less or equal. It's actually strictly less, but we don't care about that. Okay, so what you have now is, so what we now have proven is that we have this map T, and now I'm going to think about this map, on the space of y that is continuous on this interval here. And what you have is, and I'm thinking about with the norm at each point, this here is less than r. And again, this is really a ball in this metric space, but let me just write it out like this. And what you have is that, this is the space, and you have that t of y. If y is in this space, then t of y is in the same space. So t of y is also continuous on that interval, and t of y at each point x is less or equal to r. So the map mapped this space into itself, okay? Now, the next thing we want to prove is that the map is contracting, okay? You see that you need, if the space is not stable, right? So imagine that you take, we're starting with some giant metric space. This is the continuous function, say, on this interval. And then we're looking at some subspace of that. So these are continuous on a smaller interval. Okay, but this. But if and then we have defined a map. But if if somehow the map was taking us out of the space where it's contracting, then we couldn't keep applying the contracting map, right? It wouldn't anymore be, and the thing is that you want to just iterate. You want to pick some point, and then you want to keep applying the contracting map. So you want it to stay in the space where it is contracting, right? And so this is what we did in 1. But we haven't yet proved that the map is contracting. And so now to prove that the map is contracting, we're going to further restrict the interval, okay? And so I'm going to define now one more constant, sorry about that. So this is m here, and m is going to be just the max of f prime of f prime of z, absolute value of this, where z here is less or equal to r. Fine. So this is my well, almost the second last constant, unfortunately. And now I'm going to define this. So the last constant is going to be the interval that I'm going to work with, right? So remember what I'm trying to do is I have this differential equation, and I want to say that near 0, there is a solution. But near 0 just means that there exists some tiny interval around 0 where I have a solution. And again, if I have time, or else I will do it next time, I will give an example where you can see that in general, you would need to look at a very tiny interval for this to have a solution. Otherwise, it doesn't have a solution on a very large set. Okay, so I define it like this, and then I define delta here. So delta is now going to be the minimum of delta 0, the one from before, and then 1 over 2m plus 1. And now I want to look at the space. So I want to look at T, and then T is going to be a map from the continuous functions. So y here is a continuous function on now this little interval. So this interval here, because you have the minimum of this interval is contained in the corresponding interval with the delta 0. So it's y in this space such that the norm here at each point is less or equal to r. That's a space I'm going to look at, and we already know that T maps this space into itself, right? Because there's really no new statement. If the function is right, so as long as you have this here, and you apply T on it, when you apply T on a function, it's defined on the same interval. So it will automatically define on this smaller interval. And we already have this property. Okay, so T maps this space here into itself. Okay? And now I want to prove, I want to estimate, so I take 2 elements in this space. So I have y1 and y2. So you're looking at, so y1 and y2 are in this space. And you want to look at what is the distance between y1 and y2. Right, so we want this here, and we want, what I want to prove is that it's contracting. So I want to show and I want to prove, I'm going to prove it. You know, my constant C will be explicit. It will be just a half. So that certainly is less than 1. and this is what I want. Okay. So now, let's look at that. So t of y1 minus t of y2. This thing here, t of y1 is defined to be a plus the integral. Sorry, and let me write, so I'm going to, let me just make a little more space here. I worry I'm running out of time, but let's see. So this thing here, minus t of y2, and I'm just looking at the difference in some x. And again, x here is now in, x here will be in the interval. You were looking at x in the interval, in this interval. And so I'm just writing down first here what this is. This is the integral from a to x of f of y1 s plus g of s. And then you have minus, this is what you get for a2, for y2, a, so minus this thing here. So this is this difference, right? And what you see is the first thing you observe is that the a's here cancels, right? But it not only does this cancel, but this term here also cancel, okay? And that actually, there was a good reason that they were lower order. And the point here is that, right, the main point is in the unknown function anyway, right? And it's a what's called a nonlinear equation. So that's a difficulty. So, but what you then get when you write down, when you have after the cancellation, what you get is f of y1 of s minus f of y2 of s ds. Okay, so you have that. Now I will look at this thing here and that thing here, and I'm going to, and you have to now abstract. So now I'm going to look at this difference here. And then now the thing is that you have to kind of abstract from it, and you have to think about s as being, if you think about s as being fixed, right? Then this is just two numbers, right? You could think about this as set 1 and this here as set 2, right? This here as set 1 and this here as set 2. So it's like f of set 1 minus f of set 2, right? Now, the mean value theorem tells us that this thing here is equal to the derivative at some intermediate point, let's say set 3, where set 3 is between set 1 and set 2, right? And then times set 1 minus set 2, right? And, but, okay, so this is just for, for any x s, you have this, okay? But this means that now we're almost out of time. So this means that when you're looking at the norm of this, f of y1 of s minus f of y2 of s, right? That the norm here is, so the norm is equal to f prime at set 3 times set 1, which is, and set 1 I can write in, it's really this, and this is Z2. This thing here, remember Z is some point in between those 2 points, right? But both of these points here, both this one here and that one here, have norm less than R, right? So this here is, so, but now where the way that M was defined, and it should have been on the same board. So M here was defined to be the maximum of F prime of Z, where Z was less or equal to R. And so you see that this thing here, where you take the derivative, that is bounded by M, right? So this thing here is less than M y1 S minus y2 of S, like that. Okay, so I'm not sure whether we should stop. I mean, we're over, and I probably need a few more minutes. Maybe we should stop. And it's not a great place to stop, but that's how it goes. So I will keep you in suspension, and so we'll pick up from here on Tuesday. And so I want anyway to explain to you why actually this method, which seems a little crazy in a way because it's bringing in all these things, why it turned out to be basically optimal. Okay. And then we'll do a review the rest of the time on Tuesday.